Anybody remember the formula I said that you should have memorized? No? Well, that's good. But for probability relating to the intersection and the union, said there's not a lot you have to memorize, but you should memorize this. Give you a hint, it's something equals something plus something minus something else. P parentheses, A is one of the four things. What thing? Which one is it? No, not a bar. Yeah, but that's pretty straightforward, right? That one's a little bit easier than this one. That's just saying a probability of an event not happening is the probability of an event happening minus one. Yes.
And then this one is I mean, P is
Yeah, you can just read that. You can read these. By the way, P of A, probability of, yeah, plus.
P of A and B.
Yes, that's probability, right? So the probability of the union, right? A or B, right? The probability, just think about it. I'm throwing a dart at this, right? H point, let's say this is a dartboard. Let's say I have to hit the board, right? No one, if it's me, I'm definitely missing the whole board, right? Like, right? Anything that involves court, right? It's good that I'm good at math because like anything that's my hand-eye coordination is about as bad as my handwriting, right? So anything that involves that. But let's just say if I miss the dartboard, I'm throwing it again. Well, what's the probability that I hit either of the circles, right? Well, it would be the probability of hitting the first circle, press the probability of hitting the second circle. What's the problem with that? What am I double counting? The overlap, right? Because the probability, I could hit A and B at the same time, right? Right, and this part would include, so this is probability of A is right here in red. Probability of B here in yellow, right? Well, it's saying, okay, it's saying that I might hit, it's assuming that, these are disjoint, right? I'm over, right? Like that area that's both of them is counted in both, right? But you can't use the same area twice. So you have to subtract the probability of hitting both of them to find the probability hitting one or the other one, right? So this is something that you need to memorize, and it's fairly intuitive, right? If you understand what these things mean. So that was from a 4-2, right? So that was compound event, Venn diagrams. We started talking about this a little bit. I want to go over it again. And then I want to talk about this one, right? A lot of you had that, right? You found in your notes, it should be on the top of your head, right? It just needs to be mastered, right? Just like, I don't know, other facts, your address, right? Maybe the zip code, the names of the 50 states, it needs to be there, right? A union B. This is A union B. Does A intersect B? These are disjoint events. I already did this, so I'm just reviewing, right? So, and again, here's the example of using the probability for a compound, right? This is the formula I just had me memorize. Notice the formula for disjoint events isn't different. It's just, you don't have to worry about subtracting because in disjoint events, the probability of you having both of them is 0. Here's what I just started talking about. Conditional probabilities, right? It's the probability of an event based on other events, right? And typically you might think of an event that occurs after another event, right? But we're not really going to worry about, like, it can be done differently. It's just if it's known that one event has occurred or will occur, right? Right? You can still do that, right? So like This right here is probability rain if it's cloudy, right? That is probability of A given B. So if you're given it's cloudy, what's the probability it's going to rain? Perhaps that's the same thing as this. Maybe it's different, right? We're going to figure that out. Do we understand what a conditional probability is? So simply speaking, two events are independent if one does not affect the occurrence of the other, right? Two events are dependent if one does affect the other one, right? Now, students understand this conceptually fairly well, but understanding the rule or mathematically is a little bit more difficult. Okay, so this is a test, right? Either it says or, right? So if one of these is true, the other one has to be true, right? So you only really need to look at one of them, but you could look at both. So let's just think about what this is saying. So we were talking about this before. So I had Bobby come up with two different events, right? Right. One is like the Bears win, right? Like, so event E could be that the Bears win. Win what exactly? Just assume that there's one game, right? Let's just, for simplicity's sake. And event F is the Bulls win, right? Now, if let's say the probability that the Bears win, let's say that we think that that's 40%, right? You could also write that as a decimal as 4, right? These events, guys, are these dependent or independent events? Independent. They don't affect each other, right? What's the probability that the Bears win given that the Bulls win? It's 40 because they don't affect each other, right? This number was not 40. We would assume that they affected each other in some way, right? So this is the test of independence. If you have the probability of an event and you have the probability of that event given another event, right? This is easier for students to think it through this way. You're either able to see this, right? This is what this test is saying. If the probability of an event occurring is not affected, right, by another event occurring, those two events are independent. Otherwise, they're dependent. So I haven't really told you how to calculate these yet, right? But this is a way you could test. If you had these quantities, right, compare them, right? It will tell you whether an event is independent or dependent. Just notice, right? This is saying, right, I have the probability of, like, notice this doesn't change. You know that F occurs, you don't change your prediction with E. That would only happen if the two events are independent, right? So you would not expect a situation like this if E is it rains and F is it's cloudy, right? That's something you would not expect this with. So this is a test of independence, right? So if you can find out the probability of one of these things, I'm a loud talker, right? This happens all the time, right? If you can have these and compare them, you can determine whether events are dependent or independent. This is another test of independence. This one is not as obvious. But we can give some intuition to it, and then this next slide will give intuition. So either of these tests will work. So again, it's a test, right? So you need to have all three quantities have to be known, and then you can just compare the product to the probability that both occur. So we actually kind of use this Let's say I have 2 coins, right? What's the probability if I flip 2 coins that both are going to be heads? Well, let's write out the sample space. Heads, heads, tails, heads, heads, tails, tails, tails. What's the probability I'll flip if I flip 2 coins? I'll have exactly 2 heads. 1 out of 4. I can think of this as the probability, so I can write this a different way. Probability of, this means first coin is a head, and second coin is a head is equal to the probability let's see if this is true. What's the probability if I flip 2 coins, the first coin is going to be heads? Guys, you're killing me. 50% or as a fraction, everybody? What's the probability the second coin is going to be a head? We're able to multiply these like this only because the 2 events are independent, right? What happens with one coin does not affect what happens with the other one. For example, let's think of one that's, yeah.
Formula to the first one with the bulls and the bears. Or no?
Yes, if you had, yes, you could apply these to either one. It's just which quantities, how do I want to say this? Which quantities are known and unknown, right? So I don't have the probability of the bear. If I had those 3 quantities, right, I could apply. Yeah, I could test. So either time you can use this, and we will do a tiny bit of this, but this is mostly knowing that. Now, notice there's other probabilities that this would not work for. So in that scenario, I was flipping 2 coins, right? So the 1 subscript here means it's the flip. So here's a question that sounds weird. Let's say I flip 1 coin. What's the probability my first flip is heads and my first flip is tails, everybody? I flip 1 coin. What's the probability that the flip, you're doing or, it's not 50, it's not 100. I flip 1 coin. It is both, flip the coin.
Oh, yeah, 0.
Flip it. Reveal it. It's both a heads and a tails. We get to this 0. Right? These 2 events exclude each other, right? They're in fact complements, right? We get this 0 here. I'm flipping 1 coin. When it says and, that means that both events occur simultaneously. Right? Think about this. This is the intersection, right? So if A is get its heads, B is get tails, there's 2 events should not be overlapping. So the probability of getting both of them is 0, right? I know that's weird to say, but I'm trying to show this to you. But probability of getting your coin a heads, the first coin being heads is 1 out of 2, right? And the probability of your first coin being tails is 1 out of 2, right? So the product of a heads and a tails is 1 out of 4. Do we agree with that? But that's not equal to this because getting a heads and getting a tails are definitely not independent events. Right? If I get a heads, I'm definitely not getting a tails. Right? This is on 1 flip, right? those are dependent events because it's the same flip. These are independent because they are different flips, right? So we can see we can only use this product rule, right, if the two events are independent, right? But there is a product rule that takes this into account. This word means and. A symbol, I'm sorry.
Like the upside down.
Yeah.
Or-
I will not use that. Your book does not use that. Unfortunately, I have some of these slides back from when I taught finite math at Lakeland College, which does use that symbol. I need to fix this, my mistake. So this is saying, right? What's the probability of two events happening? Well, it's the probability that one of those events happens. Then you multiply by the probability of the second event happening, knowing that the first event occurred. Right? Think about that. Right? So what's the probability it's rainy and cloudy, right? I wouldn't, let's say cloudy is 1/2 of the day and rain, or 1/3 of the day. Let's say cloudy is 1/2, rainy is 1/3, right? Well, what's the probability it's rainy and cloudy? Well, if I just multiply these together, I would get 1/6, right? Because that assumes that half of the rainy days, it's also cloudy. Or alternatively, 1/3 of the cloudy days, it's also rainy. But that's not true, right? Those thirds of the days that it rains, those are overrepresented by the clouds. So you have to account for that, right? So the way you can think about it is, all right, let me just say, cloudy or rainy if cloudy. Okay. Let's see, what do you think? I think like 2/3 of the time it's a cloudy day, it rains. That's probably not right, but I'm just making stuff up here, guys. All right. So let's think about this then. Well, what's the probability? This would be raining and cloudy, right? Let me put and because you guys don't use that. Well, I know that. So I'm looking at this formula over here. It's the same thing. It's just the order there. Well, one-third of the days, 1/2 of the days is cloudy. Read this. This is F given E. This says if it's cloudy, it's going to rain 2/3 of the time. So what fraction of the days are both raining and cloudy? Well, look at all the days that are cloudy, right? Those are the E days. What portion of those days are also raining? Well, it's 2/3 of the one-half of the time is cloudy. Of that half, 2/3 are raining, right? So I'd multiply those two together. I wouldn't want to multiply by the 1/3 for rainy because those rainy days, right? It's 1/3 of the days, but they're not equally distributed over all days. That 1/3 is disproportionately focused on the cloudy days, right? This is why you have to multiply this. This is kind of an adjustment, right? Think about this as the independent adjustment, right? If you want to find the probability of two events occurring, just multiply the two events, right? But the events are independent, right? Or the events in this case are dependent. So if I know that F has occurred, I don't want to multiply by the probability of E in general. I want to multiply by the probability that E occurs. So what has already occurred if I'm in the F land? F has occurred, right? And since the two events affect each other, I want to multiply by the probability of E given F. And if you want to know, make sure that you multiply these correctly, right? Because probability of F times F given E isn't anything. Notice that the correct notation is that you can use either formula, but what is the event that's chilling on its own has to be the second event for the formula to work right. So it's P of F times PEF and P of E times FE. Questions on this formula? Yeah, what else might I be considering?
Do the events have to be like dependent or?
So these are for oh, well, if the events are independent, this formula becomes the other one. So tell me, Regina, if F and E are independent, what would F given E be the same as?
You said F given.
E, if E and F are independent. Well, E doesn't affect F, right? In that case, would be F. So this is the probability. So if F and E are independent, the probability of F given E would be the same thing as the probability of, right? So if the two events are independent, both of these reduce to PE times PF, which is only true if they're independent. So these formulas work either way. It's just that the formula is much simpler. If the events are independent, we don't have to worry about the conditional probabilities because that's just the same as the regular probability, right? Does that clear that up? All right. So I know there's a lot here, and once we do the section on conditional probability, which is going to be the second half of class today, this will be a lot clearer, right? So just take a moment, talk about this slide. What's going on with this slide? What's going on with the previous one? Talk about that with some of the people around you while I do the attendance. Does everyone understand what they're being expected to do? All right, so talk about those two slides. Just anything you can get out of them. I just made those up.
Oh.
I'm making up a scenario and thinking about how you would use that going forward. Yeah, go ahead. Yes, or I guess in that case, go forward. Yeah.
Yeah. The probability of G and the probability of P. Are you just?
Yeah. Of course. Yes, anytime.
Asking if this
Mm-hmm.
is the same thing as this.
In this case, it is, because, yeah. So Regina's asking, well, how is this the same thing as this? Yeah. So this is the probability, E and F, and we're going to do some more examples with this, is that it's raining and it's cloudy at the same time, right? Rainy and cloudy. Well, I would want to know, right? Okay, what portion of the days are cloudy? And in this case, that's the same. So what portion of days are cloudy? Do we get that that's the same thing as the probability that it's cloudy on a given day? Right? So half of the days are cloudy. And this says F given E. So this says what portion of cloudy days are also rainy, and that's 2/3. So if I said, what's the probability of it's both cloudy and rainy, you would say 1/2 of the days are cloudy. That's PE. right? And at 2/3 of the days that it is cloudy, it's also raining, right? That's F given E. So I would do 1/2 times 2/3. Notice that's the same thing here. Portion of days that are raining. Sorry, portion of days that are cloudy, and of those cloudy days, what portion is raining? I want to multiply those. So what I'm doing there, maybe this is not getting everybody. This rule I find are confusing, right? So I'm just giving you some intuition for the rule, right? That's what I'm doing here. If you memorize these rules and know when to use them, that's fine, but that's the intuition. So it is the same thing. Does that? Yeah, you need to practice this. And once we can calculate conditional probabilities, which is a lot in the next section, we're going to be doing a lot better. All right. So honestly, if
Given E times E to get the answer, to get the probability.
of both of them occurring, yes. Or you could solve, it's an equation, right? So if you know any two parts of it, you can solve for the third part, right? And we're gonna come back to these equations. There's another way of looking at them which might be more intuitive, right? It's written as a product. Actually, right? Anything that's a multiplication fact, there's a corresponding division fact. 2 times 3 equals 6. That means 6 divided by 2 is 3. We're going to have a 6 divided by 2 is 3 situation that's the same thing in about an hour. And maybe that'll be a little bit easier for some of y'all. All right. So, and we'll have another way of showing. Yeah, I got a lot of stuff for y'all. Okay. So let's try reading this. This one's actually going to use the equation that we used from earlier, the one I talked about at the beginning of class. All right, so let's try to read this. Luckily, this is a business class, statistics class, so I use a business scenario here, right? So you can look at businesses, right? So there's two events here, right? One is that a business is female owned. Oh, wait, this is not that equation, sorry. Just forget about what I said. Let's read this out loud. All right. So I have businesses being female owned, right? So I'm going to say female owned. That is represented by event F. And then just so we don't, so some textbooks always use F and E or always use A and B. I find that that's nice because you never have to change the formula, right? But I find that confusing and it's hard to remember which event is A and which event is B. So I'm going to use different letters each time. And then another thing is that the business might have 1 to 4 employees. I'm going to call that event 1-4. So let's read some of these sentences, right? So when you have something like this, you need to translate it to math. You need to translate the given probabilities to the mathematical notation, and you need to translate the I don't know what the word for it is, the probability that's being asked for to mathematical notation. So let's write it like this. The probability of that a business is female owned is 0.3595. So how do I write that? I'll give you a hint. It's going to start with P of something. It's P of what? P of F. That's the easy one. Now let's read this other part. Let's use a highlighter. Let's read the second. The probability that a business has 1 to 4 employees, given that it is female owned, is this roughly 57% number. Well, being the same color will help. Sorry, I miswrote that. That green readable in the back? Yeah, okay. This is, let me read it out loud. The probability that a business has 1 to 4 employees, given that it is female owned, is, and then it gives the number. This is probability of what? Or I said 1 to 4 in this case. Yeah, so if you want to use E and F no, you got that, Reggie. You got the answer correct. I just like to put this here because you can replace E and F with whatever letters, or in this case, it's not even a letter, right? I kind of stretching the definition there so that you can remember what it is, but you just use the formula correctly each time. Because it's very, if I made these A and B, well, one of them has the letter F in it, but if I made it A and B, it would be very difficult to remember. Okay, so those are the two given quantities. It does not. It does not. You were not here. Can anyone tell Mars, what did we learn that slash means? In one word, it is given. Independent is not given. So that means it could, yes, in this case, they would be dependent, right? But we don't know necessarily yet. Mars, this is saying, let's assume I know the business is female owned. What's the probability it has 1 to 4 employees? So it's given, right? You're going to have to read the slides at the beginning to kind of figure that out. But that's what that line means. Okay. So now what is the question that they are asking? I underlined it in. So that's what we need to find out. It's probability of something. So that would be the probability. How would I write that? Female owned and has 1 to 4 employees. Well, there's a very important word there. That's the key. And so it's going to be probability F and one to 4. So sometimes the hardest part is this, right? You have to read a story. This is how I would even solve this. I would have trouble solving this without going to the notation because I would have a hard time seeing the relationship unless it's broken down. So what's the formula that we can use here? Well, we had on the previous slide, like E given probability of E and F is the probability of E times the probability of F given E or something like that, right? So we can use that here. So let's try to do that. Probability of F and 1 to 4 is going to equal the probability of F it's again, right? You might want so this formula makes sense if you think about it. This is roughly 36%, right? And this is roughly 57%. So if I'm saying what percentage of businesses are female owned and have 1 to 4 employees, I would say, well, I know roughly 36% are female owned. And of that 36%, 57% of them have 1 to 4 employees, right? I wouldn't want to multiply if I was told 57% of all businesses have 1 to 4 employees, that number might not be the correct one to use. Because I don't know if that is represented, if those 57% is spread out equally among male and female owned businesses or not, right? So here's the thing. Jeannie asks, is this true because well, this number is only interesting because it's dependent, right? But even if it were independent, this number would be the same if I didn't have F or not, but I could still use the formula, right? It would just, so this formula works whether the events are independent or dependent. So then all I have to do is plug in the numbers I have. And I get that it's roughly 20.5% or a little more than about 21%. And notice this formula, right? When you do the scenarios, it kind of makes sense. What portion? Well, it should be 57% of the 36%. We get to a little bit of the intuition here. All right, let's do another example. So when we do these probability example, right here, here's a good way to, another way to get an intuition. So I'm going to do A on one slide and B on the other one. So let's do A. So there's a lot of drug testing examples in statistics classes. So hopefully none of you guys are these positive test results. Okay. So 50% there are subjects who use drugs. Tests aren't perfect, right? There are ways of trying to beat drug tests. I'm not going to outline them here because that would probably be like, why are you teaching your students how to beat drug tests? But all right, so this test isn't perfect, right? There's 50 people are known to use drugs, yet somehow 5 of them test negative anyways, okay? So let's say I'm randomly choosing 2 of these 50 people, right? What's the probability that the first person has a positive test result and the second person has a negative test result, right? And then in A, you are doing it with replacement. That means like you choose somebody randomly and you kind of send that person back. So you might choose them again, right? So in A, with replacement, are these the 2 choices, the first person and the second person, are these independent or dependent events? They're independent, right? Just like flips of a coin, because that person's going back. So these are independent. So the probability that I'm going to write so this means probability first positive and negative, second negative, okay? When the events are independent, I can simply multiply them. The probability that the first person is positive is 5 out of 50, right? Or 1 out of 10. The probability that the second person is negative right? This is just, the events are independent. You can just straight up multiply them, right? Let's do B though. B is without replacement. So that means I want to choose, it's going to say, if I chose somebody, I'm going to give you, I'm thinking about choosing somebody in this class as a name, but this is someone who's a drug user, so I'm not going to say that. If Steve is in this test, right, and I choose Steve first, he can't also be chosen again, right? I'd have to choose one of the 49 other people, right? So in this case, are we talking independent or dependent? If I choose a drug user, what happens to the percentage of that group that is drug users? It goes down and the non-drug users go up. So anytime you have, so key thing is anytime you have without replacement, right? The fact that someone is chosen, that whole group is disturbed at least somewhat, right? So anytime without replacement, I want you to read that as dependent. This is a dependent situation. So now to find the probability that the first is positive and the second is negative, I have to use the other formula. So it's easy to think about this in the correct order. So there's two things. I need to find out what's the probability that the first person is positive. And then I want to multiply by the probability that the second person is negative, but what do I know already occurred? The first person was positive, right? Not the second. Just to be, I think that's what you meant by I just want to be 100% clear to everybody. So this first number, do this in the right order. Yeah. Oh, I got these backwards. I was just usually more of the people test negative. I forgot that these people were known to be drug users. All right. So the first part's the same. The probability that someone's positive is 49 out of the 50. Sorry, not 49, 45, which reduces to, if I divide top and bottom by 5, 9 out of 10. Now, the probability that the second person is negative in general, if I don't know what the deal with the first person is, I would say 5 out of 50, 1 out of 10. But that's not correct here, because how many people now can be selected from now that one has already been selected? 49. And how many are negative? 5, because I didn't select any of them. So then that gets me 9 out of 98. It's just slightly different than 9 out of 100. So notice in dependent events, I would have incorrectly gotten 9 out of 100 if I did not use the fact that these two events were dependent. So this is another intuition, right? One event's already occurred. I need to use the probability that the second event will occur given that the first event occurred. So this second formula you want to use if they're dependent or so if you know they're dependent, you have to use this formula. If it's unknown, you'll be safer if you use this formula because, right? Notice this is plus sign times minus sign given plus sign. This is plus sign times minus sign. The fact these second probability is the same thing as minus sign given plus sign because they're independent, right? It doesn't matter. So you can only use this rule, right? This multiplication rule without the givens if you know that they're independent. If it's dependent or it's unknown, you have to be safe, right? If it's unknown, you would just have to be safe because this rule will count if it's dependent. And it will also work if it's independent. So you can use either. Questions here? Yeah, the dependent or yeah, unknown. Yeah, this rule will work whether it's independent or dependent. I'm also trying to give some intuition, right? Now, here's something about sampling, and I'm going to mention this now, and we're not really going to talk about it much again, but it does matter. So later we're going to do things where I say, we got all of America, I'm going to sample 1,000 people from it, right? Technically, each selection, when I'm selecting people to a sample, right, they're technically dependent events. Each person being placed into it, right? If Bobby is selected as one of the people, right, the first person to sample, he can't be selected again for the sample, right? So then, right, Emma would be more likely to be chosen knowing that Bobby's already been chosen, right? That's a problem, right? So let's say I want to choose a sample, right, of people. Technically, if the first person is male, it's a tiny bit more likely than 1/2 that the second person would be female, right? Because it's 50-50. One person's taken out, the probabilities change. But notice, even with small sizes, right? I only had 50. Notice the independent was 9 out of 100, dependent 9 out of 98. They're different, but not much different, right? So what does that mean? That means if you were sampling without replacement and your sample size is smaller than 5% of the population, you can just pretend that the sampling is independent, even though that it's strictly speaking dependent. What do I mean by that? Okay, so there are about 250 million adults. 10% of them are drug users. What's the probability that all 3 of them use drugs? Well, these are technically dependent events, right? Once I select a drug user, it's a tiny bit less likely that the second user will be a drug user. Do you understand what I'm saying here, right? Once you exclude, just like there, right? Since I've taken somebody without replacement, it technically changes it. But taking one person out of the pool that has this many people in it, the effect is infinitesimally small. So you can assume, even though it's without replacement, we can pretend with replacement. And this assumption allows us to do statistics, right? Otherwise, this would be very hard to calculate. But we can assume, all right, so to find 3 people using drugs, probability that all 3 are positive, or the probability that the first is positive, times the probability that the second's positive, times the third is positive. Technically, these events are all dependent on each other, but just a tiny bit, right? So small. So I could just say 1/10 times 1/10 times 1/10, which is 1,000. Because my sample size is so small compared to the number of people in the whole country that taking one person out of the whole country, because they're already in my sample, the changes in probability are so infinitesimal, we can just assume they don't exist. So does everyone see how that these 3 events are technically dependent? Right? But we see that the effect of them being dependent is so small, we can just use the independent assumption and we'll be fine.